So, in the last lecture we were looking at the use of correlations in balance equations. The idea was that so far what we have been deriving for balance equations is to use a balance over a differential volume and take the time rate of change of a quantity as the flux of the quantity in minus out plus any sources. And for that flux of quantity in and out, we were using Fick's law or Fourier's law or Newton's law of viscosity. These are the microscopic laws. These are valid at all locations within the fluid. Okay. On the other hand, the correlations that we had derived for different configurations, if you recall that correlations at low Beckley number, the Nusselt or Sherwood number is a constant. Correlations at high Beckley number, where we had P power half for the Nusselt number for flow past a rigid surface, and P power half for a mobile surface, and P power 1/3 for a rigid surface. Those are derived at steady state. That is, you are assuming that there is no variation in the temperature at the boundaries, or the concentration at the boundaries when those are derived. And so, those are not in general valid for time varying problems. So, therefore, we cannot use a correlation in a balance equation, because that correlation was derived for steady state. However, there are situations where you can use the correlation, and that is when the time for the evolution of the temperature or the concentration at boundaries, or the time for evolution of the boundary itself, is much longer than the time for the diffusion for the temperature or concentration field to reach steady state. Okay. So, that is what I had meant in the last time. The diffusion time is much longer than time for variation of the temperature at the the time for the temperature variation at the boundaries is much larger than the diffusion time. In the case of, for example, a sphere that is cooling in a fluid, okay, the temperature T at the surface, okay, and T infinity is far away, say, the temperature at the surface evolves because as the sphere cools, there is heat that is conducted into the fluid. And because of that, the temperature decreases. The temperature at the boundary decreases, because in case the thermal conductivity of the sphere is much larger than the fluid, the temperature equalizes rapidly across the entire sphere. So, that temperature decreases. The correlation Nusselt number is equal to 2 for the flow for the heat conduction from a sphere in the absence of flow assumes that it is at steady state. So, under what conditions can we use this correlation? For a time varying problem, we can use this correlation so long as the time it takes for the sphere temperature to change is much smaller than the time is much larger than the time it takes for diffusion to take place. Because the time for diffusion is basically the characteristic length squared by the diffusion coefficient. Note that diffusion coefficient has dimension of length square per time. So, this LC square by alpha is the time taken for diffusion, or LC square by D. Okay. So, that is the time it takes to reach steady state when you have altered the temperature on the surface of the sphere, the time it takes to reach steady state for the temperature field around the sphere. If that time is small compared to the time for the variation of the sphere temperature itself due to this conduction, then you can assume that the system is at steady state at each instant of time and use the steady correlation. Of course, you have to go back and check after you have solved the problem that the time required for the evolution of the sphere temperature is in fact much larger than the time it takes for diffusion. So, that is for time dependent problems. For problems where the temperature depends upon position, you generally cannot use a correlation, because the length scale for diffusive transport is comparable to the dimension of the sphere. Okay. So, you generally cannot use it in the limit of low Beckley number when transport is due to diffusion. and we had solved a problem for the cooling of a solid sphere of density rho, specific heat Cps, diameter d, and within a fluid density rho f, specific heat Cpf, and conductivity Kf. And if the initial temperature is T naught, we had to determine the temperature as a function of time. So, this was the energy balance equation. The change in energy of the sphere is equal to the negative of the heat that is conducted outwards, which is minus of QAV into pi d square. And for this average flux, we had used the correlation, Nusselt number equals 2. And that time we found the condition under which the correlation can be used. Okay. The time for the variation of the sphere temperature Tc has to be much larger than the diffusion time d square by alpha f, and we got this condition. Okay. We got this condition. Under these conditions, the temperature of the sphere is an exponentially decaying function of time. Okay. This approach can also be used when the boundaries are changing. Okay. So, for example, when a spherical particle is dissolving in a fluid, the radius changes as a function of time, and because of that it is not a steady state problem, okay, because the radius itself is changing as a function of time, though the concentration on the surface is equal to the saturation concentration at all instants of time. Okay. So, we had solved that problem as well. The rate of change of mass with respect to time is equal to minus of the mass flux times the surface area pi d square. We had expressed the mass in terms of the density, and finally got an expression for the rate of change of the diameter with respect to time. Recall I had said that this is actually a total derivative, but to distinguish it from the letter d that I am using for the diameter, I have used a partial derivative here. And the time it takes for the sphere to dissolve, okay, we had calculated that. Okay, that dissolution time is rho d naught square by 8 d Cs. Okay. We had calculated the surface concentration, saturation concentration in the gas phase at equilibrium with the solid based upon the partial pressure of camphor in air. And based upon that, we had got the time for the diameter of the sphere to completely decrease to 0, that is the sphere to dissolve, turned out to be more than 1 day. Okay. Whereas the diffusion time is just d naught square by the diffusion coefficient. For the diameter being 10 power minus 3, 1 millimeter, this diffusion time is approximately a few seconds, okay, 4 seconds. Therefore, this approximation is valid because the time it takes for the diameter to change is much larger than the time it takes for the diffusion of the solute to for the concentration field of the solute to reach steady state around the sphere. Okay. So, these were simple cases where diffusion was dominant. Okay. Now, let us look at some cases where convection is dominant. Okay. So, forced convection. Okay. I will first try to give you a physical picture of what goes on in forced convection, and then tell you what are the length scales for diffusion when there is forced convection. Okay. Let us say I had a sphere which was at a higher temperature, okay, T naught, okay, in a fluid which is at a temperature T infinity far away, okay, which is less than the temperature T naught. Okay. And there is a fluid flow, okay, with free stream velocity Vfs. Okay. Now, as the fluid flows past the sphere, okay, as the fluid flows past the sphere, the heat energy that is being conducted out into the fluid, okay, is being rapidly swept downstream by the fluid flow, okay, is being rapidly swept downstream by the fluid flow, and in the limit when the Peckley number is large, okay, is equal to VFS d by alpha is much larger than 1, okay, where VFS is the free stream velocity, okay, and d is the diameter of the sphere. So, let me just shift this. Okay. In this limit, the disturbance to the temperature field in the fluid, see far away from the sphere the temperature field is T infinity. Close to the sphere there will be a disturbance to the temperature field around the sphere due to the convection. That is restricted to a thin region close to the surface called the boundary layer. Okay. Okay, so, the boundary layer, it has a lower thickness on the upstream side and the thickness increases as it goes downstream. Okay. So, this is the characteristic length. Okay. So, this distance, this boundary layer thickness is the characteristic length as far as diffusion is concerned in the limit of high Peckley number, because the disturbance due to diffusion is restricted to a thin region. It gets convected downstream before it diffuses very far from the surface in the limit of high Peckley number. This is in contrast to the low Peckley number case, where it diffuses a distance comparable to the diameter. Okay. The length scale for diffusion is comparable to the sphere diameter. Okay. In this case, the length scale for diffusion is much smaller than the sphere diameter. Okay. And because of that, the length scale, the time scale for diffusion is also much smaller than the diffusion time over a distance comparable to the diameter d. Okay. So, how does this actually vary? Okay. This can be derived, I will not do it here. Okay. So, if I have forced convection around particle, okay, the in a laminar regime, and I will put this as diffusion length by LC. Okay. For laminar regime, the interface is rigid. Okay. So, this is a rigid interface for a particle. In that case, the diffusion length by the characteristic length goes as P e power minus 1 by 3. Okay. It scales as P e power minus 1/3 in the limit of high Peckley number. Okay. Note that all of this is in the limit P e is equal to VFS d by alpha much greater than 1. That means the length to which the heat diffuses is P e power minus 1/3 times the diameter of the sphere. Okay. Around bubble. This could be laminar, okay, or laminar flow in both the limits of high Reynolds number and low Reynolds number. Recall that forced convection around a particle, it is the laminar flow is only at low Reynolds number. At high Reynolds number, you have formation of a separation bubble at the rear, then formation of a wake with vortex shedding, and then a turbulent wake, and so on. This scaling law that I have derived for you is only for laminar flow. Okay. okay, at low Reynolds number. For a bubble, recall that you have a laminar flow even at high Reynolds number, provided the interface is mobile. There are no surfactants which tend to make the interface rigid. Okay. So, this is a mobile interface at which the zero stress condition, here the zero velocity condition, no slip condition is applied. Okay. Here the no slip condition is applied, whereas for a bubble the zero stress condition is applied. And in this case the boundary layer thickness goes as p power minus 1 half. Okay. So, it is 1/3 for a rigid interface and minus a half for a mobile interface. Okay. Flat plate, okay, forced convection, flat plate. Okay. Once again this is for a laminar flow. Okay. Okay. And note that in the case of a flat plate, generally the Reynolds number is much larger than 1. Okay. And we have a rigid interface, and in this case it is equal to Re power minus 1 by 6 P power minus 1 by third, okay, or Re power minus half PR power minus 1 by third. Okay. Okay. And this works for laminar flow around a flat plate, okay, in the limit of Re much greater than 1. Okay. Now, forced convection, falling film. Okay. Note that this was mass or heat transfer to a falling film at a mobile interface, zero stress condition at the liquid gas interface. Once again laminar. Okay. This is mobile interface, zero stress. Okay. And this goes as P power minus half H by L power minus half. Okay. Where in this case L is the length of the film and H is the thickness. Okay. So, recall that we had considered a film, okay, at a rigid surface. Okay. You had a parabolic profile. Okay. H was the thickness of the film, it was falling due to gravity, and L is the length. Okay. This is equal to H by L power minus half, okay, or L by H power half, okay, or L by H power half. So, this thickness increases as the film length increases, and it goes as P power minus half. So, obviously, this film thickness will be much smaller than the thickness, this diffusion length will be much smaller than the film thickness only when H by L is L by H is much smaller than P. Okay. Otherwise, this thickness will become comparable to the thickness of the film. Okay. This diffusion length will become comparable to the thickness of the film, and then we can no longer use this approximation for the diffusion length. Okay. Similarly, for a pipe flow, laminar with a rigid surface, no slip condition, the thickness is P power minus 1 by 3 into D by L power minus 1 by 3, okay, where D is the diameter and L is the length. Okay. So, recall that for a pipe flow, the diameter was D and the length was L. Okay. So, these are the diffusion length. Okay. So, in the film thickness, for example, diffusion is limited to a thin region close to the surface. Okay. Similarly, for a pipe flow, the diffusion from the walls, okay, the heat transfer from a pipe, for example, from the walls is restricted to a thin region close to the wall of the pipe. Okay. And the thickness of this region divided by the pipe diameter is given by this. Okay. And so, because these are restricted to thin regions, the diffusion time is also much smaller for these cases than it is at high Peclet number. Okay. So, the diffusion time is equal to the diffusion length square by the okay. So, for example, this for this particular case, okay, where the diffusion length goes as the characteristic length times p power minus 1/3. So, this will be okay, p e power minus 2 by 3 L c square by alpha. Okay. In the diffusion dominated regime, the diffusion time was just L c square by alpha. Okay. Here the diffusion time is p power minus 2/3 time L c square by alpha. Okay. So, it is actually much smaller in the convective regime, because the diffusion has to take place only over a relatively small region here. Okay. The diffusion has to take place only over a relatively small region at high Peclet number, okay, as the surface as the boundary condition at the surface changes. Similarly, in this case for the falling film, the diffusion has to take place over a distance much smaller than the film thickness, or in this case the pipe diameter. Okay. Because of strong convection, any diffusion from boundary surfaces is rapidly swept downstream, and therefore material diffuses to only a small distance, much smaller than the characteristic diameter, into the fluid. Okay. And therefore, the diffusion length is much smaller than the characteristic length in all of these cases, where the characteristic length is the diameter for particles, it is the pipe diameter for pipe flow, it is the film thickness for a falling film, and it is the length of the plate for a flat plate. Okay. So, in these regimes we can assume, provided the time for variation of the temperature or concentration at the boundaries, or the time for variation of the boundaries itself, in case a particle is dissolving, for example, provided that time is much longer than this diffusion time, okay, we can assume that the system is at steady state. So, let us take the example of natural convection, forced convection of heat from a sphere. Okay. A steel sphere of diameter 1 centimeter with initial (300° centigrade) is cooled in a stream of cold air at 0° centigrade with free stream velocity 1 meter per second. Okay. What is the time taken for temperature to decrease to 100° centigrade? Examines the steady state the 500. Okay, and we assume that the thermal conductivity of the sphere is sufficiently large that the temperature is uniform inside the sphere. Okay. So, what we have here is a steel sphere at initial temperature Ti is equal to 300 degrees centigrade, stream of cold air coming in at 0 degrees centigrade and 1 meter per second, okay, going past this. Okay. And you have to calculate how much time it will take for the temperature to decrease to 100 degrees centigrade. Okay. So, first thing we have to estimate what is the Peclet number. Okay. So, for this we need the diffusivity of air. Okay. The thermal diffusivity of air is the thermal conductivity by rho Cp. Okay. The thermal conductivity is 2.4 into 10 power minus 2 watts per meter per degree centigrade into divided by the density, which is 1.25 kg per meter cubed, into the specific heat, which is 10 power 3 joules per kg per degree centigrade. Okay. And you can verify that this number, it will ultimately have dimensions of length square per time, okay, if you do the calculation, because I have a 1 over meter cubed here and a 1 over meter here, okay, meter cubed. Watts per joule is 1 over second, watt is joules per second, okay, kg will cancel out and degree centigrade will cancel out. Okay. And this gives you a value of about 520.83. Sorry, this gives you a value of meter square per second. Okay. As I told you, the thermal diffusivities in air are generally of the order of 10 power minus 5 meter square per second. All diffusivities, mass, momentum and energy diffusivity, they are all roughly of the same order of magnitude, 1.92 of 10 power minus 5 meter square per second. Based upon this, the Peclet number is equal to Vfs times the diameter of the sphere divided by the diffusivity of air, which is 1 meter per second into 1 centimeter, that is 10 power minus 2 meter. Okay. This is 520.83. So, in this case the Peclet number is large, okay, and therefore, we can use the correlation for the Nusselt number valid for high Peclet number. Okay. And the correlation that I will use is one that I had previously given you. Okay. Nusselt number is equal to 0.992 Pe per minus 1 by 3. Okay. If you recall that in the limit of high Peclet number for laminar flows, this was the correlation that I had said applies, okay, the limit of high Peclet number for laminar flows. Okay. So, I will use this correlation and try to estimate what is the time it takes for cooling, and then we will come back and verify that the time taken for cooling is actually much smaller than the diffusion time. I will continue this in the next lecture. I will see you then.